This is the implementation of the EEPROM to the 4-bit counter. Its final purpose is to output the next address of the 16-line CHUMP program. Here it is executing the Feinberg program. To further show its capabilities, this also demonstrates it controlling a 7-segment output to display a hexadecimal count. An EEPROM, or electrically erasable programmable read-only memory, is a byte memory storage device that can be programmed, read from, and written to. To access all 2048 bytes of memory in this EEPROM, these address inputs are used. There are 11 inputs, as 2 to the power of 11 is 2048. Since the CHUMP code is only 16 lines, the first 4 address inputs are used to access the first 16 bytes of storage in the EEPROM, which are connected to the 4-bit output from the counter. On top of this, a switch is used on the 5th bit to switch between the 2 CHUMP codes, where Feinberg's is stored on address 0 to 15, and the hex counting is stored on addresses 16 to 31. All addresses in an EEPROM initially come blank, so this EEPROM programmer can be used to write every byte of storage within an Arduino Nano. Before it writes to any byte, the entire EEPROM is cleared, which is what's being shown in the top left corner. Here, the first line represents the first 16 bytes written on the EEPROM, which is Feinberg's program. The second 16 is a 7-segment mapping. Because of limited pin space, the Nano is not able to have one pin connected to every address while having one pin directly connected to every I/O port from the EEPROM. So, bit shifting and 2 595s are used to control the addresses. Next comes the code. The purpose of this code would be to write a 16-line program to one of the 128 possible pages on the EEPROM. The code consists of multiple functions. However, this video will only go through the essentials, which are set address, write EEPROM, write program, and erase EEPROM. The purpose of set address is to activate the desired address on the EEPROM so that its I/O pins would either read or write to that address. Next, the Boolean variable outEnable determines whether the EEPROM will be written to or read to. To shift out these bits, the shiftout function is used, which will shift the data to the 2 595s, which will then be connected to the EEPROM. Though the 2 595s together can control 16 bits, only 12 are needed, 11 for the address, and 1 to determine read-write. The first 8 bytes that are shifted out, which will eventually finish on the low byte, contain the last 3 bits of the 11-bit address. It does this by shifting out address bitshift-write 8, which is then ORed with a ternary statement to determine read or write. If outEnable is high, then it is ORed with 0x00, which will change nothing. But if it's low, it will OR with 0x80, which will make the LSB high. This last bit is then connected to the EEPROM OE pin. Then, the second half of the address is shifted in, which will move this first byte, originally in the first register, to the second. And the first 8 bits of the address will then slide into the first register. Next, the function write EEPROM uses set address to activate the desired address, then program all 8 bits in that address. It does this by using the 8 pins on the Arduino that connect to the I/O ports, and writes each bit to its corresponding output. The LSB of the data byte is the first bit, connected to EEPROM pin 0. During each iteration of the for statement, by default taking the LSB of the data byte, it will AND that bit with 1, so that the data will stay the same. Then, it bit shifts the data write by 1, setting up the LSB for the next loop iteration, which will write to the second pin. This process will run through until all bits have been shifted. The next function is write program, which essentially uses the write EEPROM function 16 times and writes the corresponding byte to each address, where the function requires a 16-byte array. The last function is erase EEPROM. The function goes through all 2048 bytes in the EEPROM with a giant for loop and writes every bit high with 0xFF. Together, these functions can be used to wipe out the EEPROM, write Feinberg's code to the first page, and a 7-segment map to the second page.